Okay, so on Wednesday we were talking about section 7.5, and this is over indeterminate forms and something called L'Hopital's rule. And indeterminate forms, you should remember, are things like this. So they're expressions that look like numbers, like 0 over 0 or infinity over infinity, but they're not actually numbers. You can't actually divide by 0. Infinity isn't actually a number, so you can't multiply or divide by it. And so for various reasons, all of these expressions are not really numbers, but where they show up in calculus is in limits primarily. So we started by looking at limits involving 0 over 0, and that's where we got L'Hopital's rule here. Okay, and it sounds like someone's microphone might be open. Just double check yours and make sure it's muted unless you're asking a question. Thank you. Okay, so the idea here is that if you had one of these indeterminate forms 0 over 0, so your function value on the top and the bottom is both 0 if you plugged in x equals a, then instead of looking at the original limit, which is indeterminate, we can replace f and g with their own derivatives. So this limit f over g becomes f prime over g prime. And then a lot of the time, taking the derivatives allows us to finish off and actually find the limit that we're trying to compute. And then last time we did several examples where that worked out. And I should remind you that sometimes you might need to use L'Hopital's rule twice. So that's what we had to do in this example here. We started with this limit as x goes to 0 of x minus sine x over x squared. And when we took one derivative of the top and the bottom, we still had a 0 over 0 indeterminate form. So we had to take a second derivative to get sine x over 2 before we could actually find the derivative, actually find the limit to be 0. And that's something that you're going to run into on your homework. You might have to apply L'Hopital's rule more than once. And then just a couple more things. We saw that L'Hopital's rule applied to one-side limits, and it also applies to infinity over infinity indeterminate forms. So 0 over 0 and infinity over infinity. And this, I believe, is where we finished off on Wednesday. And we're going to continue on the next page of the notes here with another example. Okay. And it looks like a few more people came in. And at the beginning of class, I was asking if anyone had questions over the homework that is due later today at midnight. So if any of you that came in a little bit late have questions, then you can go ahead and ask those. Because I am happy to answer your homework questions, or at least a few of them, during class time, since you guys actually doing the problems is the most important thing here. Okay, so it doesn't sound like anyone is asking anything, but please feel free to interrupt me later on if you do think of something. So continuing with my examples of infinity over infinity indeterminate forms, if we look at e to the x, the exponential, natural exponential function, we know that this function blows up. It gets bigger and bigger as x goes to infinity. This is something that we saw a little bit earlier in the chapter. And we also know that if we plug in large numbers down in the denominator and then raise them to the sixth power, those are also going to blow up to infinity. So this particular example is another infinity over infinity indeterminate form. Okay, so since this is an indeterminate form and we know how to find the derivatives of both of these, it's an infinity over infinity indeterminate, and we know how to find the derivatives, then we can apply L'Hopital's rule. What's the derivative of e to the x? Right, Matthew, that's correct. We are going to have to apply it more than once. And I guess you can see why. Every time we take a derivative of e to the x, we get another e to the x. It is its own derivative. And in the denominator, we're going to use the power rule. We get a 6x to the fifth power. And like Matthew noticed, we still at this point have an infinity over infinity indeterminate form. So we have to use L'Hopital's rule again. So we take the derivative of the top, we get it e to the x, of course, and the derivative of the bottom, use the power rule again. 6 times 5 is 30. And then we get an x to the fourth power. And, well, that'll just keep on happening. We still have an infinity over infinity. And like Matthew noticed in the chat, we're going to have to actually use L'Hopital's rule 6 times. So in order to get rid of all of these x's, the 6 x's, we need 6 derivatives. So I don't want to write all of that out. I just want you to think about what would happen. So what would you get in the bottom of this after you apply L'Hopital's rule? You'll get a constant, right? And what number would it be? Can you tell? Something large? Right. So if you can keep track of what's going on, when we take a derivative of x to the 6, we multiply by 6 in the front, decrease the power. Then we multiply by 5. On this second step, we'll multiply by 5 in the front, decrease the power. Over here, we're going to multiply by 4, decrease the power. And then if you think about what happens in this part that I haven't written out, we'll multiply by 3, multiply by 2, and then multiply by 1. And yes, that is the correct answer, 720. What I was hoping one of you would come up with is this, though. So this is 6 factorial. And if you haven't seen factorials in a while, what they do is they tell you to start at this number and then multiply all of the integers counting down to 1. And these come up a lot when you're doing probabilities, and they also come up a lot when you're doing derivatives, like we're doing here. Okay, and what about the numerator? When we continue taking derivatives of e to the x, what will we get? Anyone?
E to the x.
Right, because the derivative of e to the x is always just e to the x, no matter how many times you take the derivative. Good. So now we have our limit. As x goes to infinity, we have an e to the x in the numerator and a 6 factorial, or 720, in the denominator. What is this limit? Can we do it now? Well, think about it. E to the x is still going to get, excuse me, allergies. E to the x is still going to get larger and larger, and we're just dividing by a constant now. So this thing is going to blow up to infinity. And maybe now would be a good time to pull up a graph. Get a window open here. Okay, so here is my graphing calculator, and maybe I'll graph our original function, e to the x over x to the 6th power. And we're taking the limit as x goes to infinity, so we totally ignore anything that's happening here, and then just look to see what's happening as we move off to the right. And well, if you already have the graph in front of you, you can kind of just see what's going to happen. If you zoom further and further out, you can see that it gets bigger and bigger. So like I said, that's easy to see from the graph. It was not so obvious just looking at the formula. And what we ended up looking at was what happened after we took several derivatives, e to the x and then 6 factorial. And the graph is roughly similar. But you can see that the blue graph is actually quite a bit simpler than the red graph. The red graph had this extra vertical asymptote at 0. So it's a bit more complicated. And this new function, after we take 6 derivatives, is much simpler, both in its formula and in its graph. And we can see that the blue function also blows up to infinity very quickly, even faster than the red function. Okay, any questions over that example? Okay, so let's go on to some more kinds of indeterminate forms. And the thing that I need to specify, I guess, at this point, is that L'Hopital's rule only applies to the 2 forms that we've seen. So it only applies to 0 over 0 and infinity over infinity indeterminate forms. All of the other forms that we saw on the first page, like 1 to the infinity power, infinity minus infinity, all of those, L'Hopital's rule does not apply, or at least not directly. We have to do some extra work. So let's take a look at a couple of those other indeterminate forms. This one is a limit as x goes to 0 from the positive side, and we have x times the natural log of x. And since we already have a graphing calculator open, let's just look at both of those functions. So that we can tell what is happening. So y equals x, that's the familiar line going through the origin with slope 1. And then the natural log is a little bit more unfamiliar, but I think we've had a good introduction. And that's this purple line. And remember, it can't ever have negative values of x because it's undefined over there. What happens is, as it gets closer and closer to x equals 0, the value of the natural log is going to get closer and closer to minus infinity. It's going to get larger and negative. So going back to the notes, what we're looking at is a function x that's going to get close to 0 as x goes to 0. And then the natural logarithm is going to get close to negative infinity, or it's blowing up to negative infinity, I should say. So we're looking at a 0 times negative infinity indeterminate form. And this particular form is not one of these two. It's not a 0 over 0. It's not an infinity over infinity. So we can't just take a derivative and use L'Hopital's rule. We have to do something different. What we have to do is rewrite this function, x times log x, as one of these two. Let's see. So rewrite, and in this case, I'm going to rewrite it as an infinity over infinity. And let me explain what I mean by that. How can I change 0 times infinity to infinity over infinity? I'm sure you're wondering. And what I'm going to do is take this x and flip it into the denominator. So x is equal to dividing by 1 over x. Oops. That's just an ln. So I keep the natural log on top of my fraction, and in the denominator, I'm going to put a 1 over x instead of multiplying by x. But they're the same. But now that we've done that, the numerator is getting, well, we already saw the graph. It's going to minus infinity. And now the denominator, 1 over x, that's going to go to infinity as well. We can just go over to the graph. I'm sure you already know what 1 over x looks like, but pictures always help. So the black graph is 1 over x, and you probably remember that this has a vertical asymptote at x equals 0. Okay, so this is getting a little crowded, but now we do have an infinity over infinity indeterminate form. And that means L'Hopital's rule applies now. We take the derivative of the top, we get a 1 over x. And then we take the derivative of the bottom, 1 over x, and we get minus 1 over x squared. And now it's just a matter of cleaning this up. Dividing by a fraction, you should remember, is the same as multiplying by the reciprocal. So I'm actually multiplying by negative x squared. And this simplifies to just minus x. And x is going to 0 from the right side, from the positive side, but doesn't matter a whole lot in this particular case, since this is a very simple function, just a line with slope minus 1. So this comes out to 0. Okay, any questions over that example? Okay, sounds like we're good. Okay, so the next kind of indeterminate form is the 1 to infinity and 0 to the 0 forms. So that's what I mean by indeterminate powers. And the technique for doing these is a little special. It involves logarithms. And here's the mathematical way to say this. The technique that we're going to do. If the limit as x goes to a of the natural log of your function, f of x, is equal to L, so L for limit, then the limit of the original function as x goes to a is e to the L. So the way that this is written out is a little bit backwards from the way it's going to work in practice. What we're going to do is we're going to start with a function, f of x, like this one, that's going to be an indeterminate power, one of these guys. And then what we're going to do is take the natural log of the function, find its limit, and then plug it back in over here. So we kind of start here, work back this way, and then finish off. Okay, So this first example, we're finding the limit as x goes to 0 from the right side, from the positive side of this guy, 1 plus x to the 1 over x. And if you think about what happens if you would try to plug in the limit inside here, inside the parentheses, you'll get a 1 plus 0. So that's a 1. And in the exponent, 1 over x, you're trying to divide by 0, essentially. So this is going to blow up to infinity. That means this particular example is a 1 to the infinity indeterminate form. And that means we're going to have to use this technique. So instead of looking at this original function, which we can't really find the limit for because it's indeterminate, we're going to instead look at the natural log of the function. And then we're going to see how that helps as we work. Okay, so let me just write down, take the natural log of your function. One plus x, the 1 over x power. And then compute the limit that way. Let's see, I guess I need to work down here so that we actually have room. We're going to do the limit as x goes to 0, and then we're going to take the natural log of the function. Okay, so all I've done is I've taken the original function, and instead of doing that, I'm finding the limit of the natural log of it. And the magic, the technique, comes from one of the properties of the natural log that we've learned. It tells us, one of the properties tells us that instead of leaving an exponent inside of the natural log, we can instead bring it to the front and write it as multiplication. So what we've done is gotten rid of the exponent, like so. Excuse me. There should be a 1 plus x in here. Okay, so the way it's written here, we have something like an infinity times a minus infinity. But of course I can just put this x in the bottom of my fraction, and then it'll be written as an infinity over infinity in determinate form. Excuse me. That's not what I mean. This is going to 0. We're not taking a limit at infinity this time. I was thinking about one of the last examples. 0 over 0. But L'Hopital's rule still applies, of course. The derivative of the top, we do 1 over what we find inside the parentheses. We're doing the chain rule, essentially, but only for the top of the fraction, since we're applying L'Hopital's rule. So we get a 1 over x plus 1, or 1 plus x. And then you would need to take the derivative of this guy, but that's just 1. So we don't have to worry about the inner derivative. Okay, and then the derivative of x is 1. At this point, we can actually just plug in 0 since we're not dividing by 0 anymore. And if you work that out, you're just left with a whole bunch of 1s. 1 divided by 1 divided by 1. So that comes out to 1. Okay, so at this point, we actually have one more step to do, even though we've already done a kind of complex limit, right? We had to use this natural logarithm property and then do L'Hopital's rule to get 1. But this is not our answer, because remember, we've taken the natural log of the original function. We're at this step. So that means we have to plug our limit. Let's zoom out a little bit here. We have to plug in our limit that we found into this. So the limit as x goes to 0 from the right side of the original function 1 plus x to the 1 over x power, that's actually equal to e to the exponent of whatever limit we found here. So that's e, and then we're going to plug in 1 in the exponent. Okay, so that's just e. Okay, so first of all, are there any questions over that example? No? Okay. So one thing I want to mention before we do the next example, if you plan on continuing your math studies, like you're a math major and you go on to take Introduction to Analysis or the second analysis course, this limit, which we just showed is equal to e, is sometimes used as the definition of the number e. So in this particular class, we had a kind of complicated definition for the natural logarithm, and then we use that to define the number e. Sometimes you do it the opposite way. You have this kind of complicated way of defining e, and then use that to define the exponential function. So that's just an aside. We're just doing limits, really, in our calculus class for now. Let's do this next one. We're going to find a limit as x goes to infinity of x to the 1 over x power. What kind of form is this? What kind of indeterminate form? Well, the base of our exponential here, that's just going to blow up to infinity, right? And then the exponent, the 1 over x, that's going to be getting smaller and smaller as we plug in large numbers. So this is going to 0. And this is the other indeterminate power form. I didn't mention it at the top. This is an infinity to the 0 indeterminate. So we're going to have to use the same technique that we did up here. We need to take the natural log of this guy, find its limit, and then plug it back in using the exponential function. So first, the limit as x goes to infinity of the natural log of x to the 1 over x. We can do this by pulling the 1 over x to the front. Or writing it this way. Let's see, is this one of the limits that we've already done? No, I guess I left this one off. We did one close to this. But this is a L'Hopital's rule problem now. As x goes to infinity, the natural logarithm blows up to infinity, and so does x, of course. So we started with a infinity to 0. Now we have an infinity over infinity. So that means we can actually use L'Hopital's rule at this point. The derivative of the natural log, as we know, is 1 over x. The derivative of x is 1. So what we're really looking at is the limit as x goes to infinity of 1 over x. Dividing by 1 doesn't really do anything. So this comes out to, anyone? Zero, yeah, that's right. Okay, so we did the first step of our technique. We found the limit of the natural log of our function. Now we have to plug it back in. So the original limit for x to the 1 over x, we can do using this limit. It's just e to that power. And what is e to the 0?
1.
It's 1, right? So that's the answer. As x goes to infinity, this function x to the 1 over x gets closer and closer to 1. Let's go ahead and take a look at the graph to confirm. Okay, so let's clear off this mess from before and just look at x to the 1 over x power. and maybe adjust the y range. Something more reasonable. So we can see what happens here. So the function has this kind of kink in it where it tries to blow up really fast, and then it levels off to 1 as you go further off to the right. Never quite reaches 1, gets closer and closer. Okay, any questions over that second example? Okay, so I have one more problem that I want to do. I wasn't sure if I would have enough time, so I didn't have it on the actual note sheet that I posted. Okay, so this is what I want to look at. The limit as x goes to 0 of 1 over sine x minus 1 over x. So the problem with this one, if we plug in 0 for x in the first fraction, we know sine of 0 is 0. So we're trying to divide by 0. That means this thing is going to blow up to infinity. And we also know that 1 over x is going to blow up to infinity. So what we're looking at is an infinity minus infinity indeterminant. Indeterminate form. So the approach to this one is a bit different than the others that we've seen. What we can do, since we have two fractions, is to find a common denominator. So that's what we'll do. Essentially what we have to do is combine the two denominators. So this one has just sine x, this one has just x. So the common denominator will be x times sine x. So the first fraction is going back to the grade school finding common denominators. You multiply by x over x. The second fraction will need to multiply by sine x over sine x. Okay, and then just think that through. We're going to get an x up here. We're going to get a negative sine x over here. And then in the denominator, we're going to get an x times sine x. Now, think about what would happen if you plugged in 0. You would get a 0 on the top, and then you would get a 0 times 0 in the denominator. So this is a 0 over 0 indeterminate form instead of the infinity minus infinity that we started with. That means we can actually use L'Hopital's rule now. And it looks like it's right at 9:50, but I'm going to go ahead and finish this problem since it shouldn't take too long. Just find the derivative of the top and the denominator, the numerator and the denominator. You get 1 minus cosine x up top. In the denominator, you'll have to use the product rule since you're multiplying two functions. So it ends up being sine x plus x cosine x. But think about it. If you plug in 0, you still get a 0 over 0 in determinant form. That means we have to do L'Hopital's rule again. Up top, we'll get a positive sign. And then in the denominator, we'll get a negative cosine. And then we'll have to do the product rule again. Okay, might have cut out there for a second. We have to do the product rule again, so we get a plus cosine minus x sine x. Let's see. I don't know why I put a minus sign here. That's the derivative of sine x is, of course, just positive cosine. Okay, and at this point, you can plug in 0. Up top, you'll get a 0. Here, you'll get a 1 plus 1 minus 0. So you get a 0 over 2, which comes out to 0. Okay, and I really do have to stop there since we're over time.